We are now looking at the elastic properties of solids. That solids like this one I'm having here can expand and return back to its original shape and size. And things like springs can be contracted or expanded and they still come back to their original shape and size. We are going to be looking at what is elasticity. So let's start by that. Elasticity is the ability of a substance, in this case a solid, to return to its original shape and size after being distorted by an external force. The distortion may be extension, that is expansion, or contraction. So that is what elasticity is. So we talk about elastic materials, and we'll say from the definition of elasticity that elastic materials are those materials that can return back to its original shape and size after the distorting force has been removed. Okay, so talking about elasticity and extension and returning to its shape and size, we now talk about Hooke's law. Hooke's law. Hook like this. Hooke. Hooke. So Hooke's law. Hooke's law states that the extension of an elastic material is directly proportional to the applied force or load, provided that the elastic limit is not exceeded. That is, that the applied force or load on an elastic material is directly proportional to the extension produced, provided that the elastic limit is not exceeded. So Hooke's law can be stated as the force or load is directly proportional to the extension E of the elastic material, provided that the elastic limit of that material is not exceeded. So having this, we have that force is now equal to, force or load is now equal to Ke, where K is a constant of proportionality called force constant or stiffness of spring or stiffness of elastic material. So we can have that force constant K as equal to the extension goes over to this place. We now have force over extension. And since force is in Newton and extension is in meters because it's a length, we now have that force constant, the SI unit of force constant is Newton per meter. Okay, so we'll still be using these formulas, these derivations from Hooke's law to solve some questions by the end of this video so that we can understand better. So we mentioned that in Hooke's law, so let me state that again, that Hooke's law states that the applied force or load on an elastic material is directly proportional to the extension, provided that the elastic limit is not exceeded. So we talk about elastic limits being exceeded. What if it's exceeded? What happens? So this leads us to force extension graphs. That is a graph of force or load on this side, force in Newton, and we now have extension in meters on this side. So we talk about this graph. We have this straight line and a curve goes down, extends, and then we now have this point, and we could even extrapolate. Okay, so let us mark some important points on this graph. We have this point, we have this point, this, and then finally. So I like to remember the points on a force extension graph of an elastic material with please ensure you move back. So if you want to keep being an elastic material, please ensure you move back. That is, ensure you move back to your original shape and size after this external force has been removed. But okay, aside that doesn't make sense really. But what does it mean for us? P stands for proportionality limit. So this is what we say, provided that the elastic limit is not exceeded, the applied force or load is directly proportional to the extension on an elastic material. So we can see that this is a portion of this portion from 0 to this point P, proportionality limit. We have a very, very straight line. So meaning that that's the proportionality. According to how much force we apply, that is the extent of extension we are going to see. And then the next point on the graph is E. We call it elastic limit. Elastic limit. So this is the point beyond which, like if the applied force, beyond which the applied force, that is beyond, we mean this way. If we keep on adding more force, and go beyond this point, the elastic material will not return to its original shape and size. Provided that the elastic limit is not exceeded, the force applied is directly proportional to the extension that will be obtained. So beyond the elastic limit, the elastic material cannot return to its original shape and size. We notice that sometimes in rubber bands, whereby due to overusage, yes, it's still elastic, but it cannot return to that original shape and size when it was new. So that is what we call elastic limit. And then this Y will stand for yield point. Yield point. So the yield point is when the elastic material has yielded every aspect of its elasticity and then becomes plastic. Beyond the yield point, the elastic material becomes plastic. It's no longer elastic. Like when we extend it, any force applied to it deforms it. Like it remains at that shape. That is what we call plasticity. It remains at the shape whereby the force left it at. If the force extended it, it will remain in that extension state. If the force compressed it, it will remain in that compressed state. That is beyond the yield point. It has yielded every elasticity it has. But between this elastic limit and yield point, the material still has some level of elasticity, but it can't return to its original shape and size anymore. It has been deformed, but it is still elastic. I hope you understand. Okay, so the next point on this graph is M. That is maximum load. Point of maximum load. That is the maximum force that elastic material can bear. So beyond the maximum load, the material starts to give way until we have our point B, the breaking point. So at point B, the material just breaks. Like if I keep extending this, that is applying some force, at some point it just breaks. So that is point B. So I hope you note down how to remember all these special points on a graph. You just plot the graph, draw a straight line, make it curve a little bit and then dip a little, and then we have this big curve that goes beyond this first curve, and then we have a breaking point. So we say, please ensure you move back. That is for you to keep on being an elastic material. Oh, solid, please ensure you move back. This is just an acronym for you to remember the points on a force extension graph of an elastic material. And then after that, you should be able to know proportionality limits, elastic limits. Beyond this, like when we get to this point, we can still return back to original shape. Beyond this material can't return back to the original shape. The yield point. This is the point that divides elastic material from plastic, like elasticity from plasticity. Beyond this, that is yielded every aspect of its elasticity. Beyond this point, this material is no longer elastic, it is now plastic. So on this plastic side, more force can still be added, like more force, extorting force, distorting force can still be added to this material. Then we have our maximum load, and then beyond that, like the material is just managing, is about to give way. Then we now have a breaking point. The material is no longer there. Everything has broken. The center cannot hold because things have fallen apart. Okay, so this is the graph. And then from this graph, let's talk about something we call Young's modulus of elasticity. Young's modulus of elasticity. So Young's modulus of elasticity is simply the ratio of stress to strain of an elastic material. So what is Young's modulus of elasticity? Or sometimes it's called elastic modulus. It is the ratio of stress to strain of an elastic material. And Hooke's law can also be defined another way. We can use stress and strain to define Hooke's law. So we can define Hooke's law as, provided that the elastic limit of an elastic material is not exceeded, the stress is directly proportional to the strain of that elastic material. Okay, so now let's talk about stress. Stress is the ratio of force to cross-sectional area of that elastic material. The ratio of force, applied force, to cross-sectional area of the elastic material. So if we have an area like this and we apply some force on it, it's going to be stressed. The more force we apply, the more stress. But if we apply that same force to a bigger area, we are going to notice that we will have lesser stress. So the more force, the more stress. But the more area and force is maintained, that is the lesser stress we are going to get out of this material. And this force extension graph can also be plotted using stress to strain. That is stress-strain graph. Will still have the same shape, and all these points on the graph will still remain the same with their meaning intact. Now let's talk about strain. So strain is the ratio of extension to the original length of the elastic material. So when you're asked to define any of these, you simply define it as, this is the ratio, Young's modulus or elastic modulus is the ratio of stress to strain of an elastic material. Stress is the ratio of applied force to the cross-sectional area of an elastic material. Strain is the ratio of extension to the original length of an elastic material. So we just define by mathematical relationships. Okay, so finally, before we go over to calculations, we now say, since when we extend this and we allow it, especially a spring, when we compress it with a weight and we lift it, we normally notice the energy with which it bounces off. So we say that energy can be stored in a string. By extending it or by compressing it, you have stored some amount of energy. Remember, we said that energy can neither be created nor destroyed. Instead, it can be transformed from one form to another. So that energy used to compress it or extend it has been stored by that spring. So energy stored in the spring, or we say work done in extending a spring or work done in compressing a spring. So whether it is work done or energy stored, we do some work in extending it or compressing it, and then the spring itself stores that energy with which we use to do that work of extension. So whether we say work done by a spring or energy stored by a spring, we still mean the same thing. So we say work done by a spring or energy stored in work done in extending a spring. So we say work done by a spring or energy stored in a spring, or let me say in an elastic material generally. It mustn't be a spring. Elastic material is equal to half Fe. That is half the applied force times the extension, or sometimes it's equal to half Ke squared if you're given the force constant. So in this case, you now have the extension squared. Now let's go over to calculation examples to see how we can use some of these formulas that we have had in the course of studying elasticity of solids. Okay, we now have this question. A spiral spring extends from a length of 10.00 cm to 10.01 cm. When a force of 20 Newton is applied to it, calculate the force constant of the spring. So let's write out our parameters. From a length of this to this, that means this was its original length. We are going to call that L sub O or sub 0, its original length when no force was applied to it, is equal to 10.00 cm. And then we have it extends from this original length to this new length. This new length, let me call it L1, the new length 10.01 cm. And then the applied force 20 Newton. And we've been asked to calculate the force constant K. Okay, so for us now, it's important that we are going to find the extension, because K is equal to F over E, force over extension. So extension is equal to the new length minus the original length. Okay, so we have it as 10.00 minus 10.01. We have it that the extension is 0.01 cm. And this is not the SI unit, so let's work with SI unit. And how do we get that? By dividing this by 100. And when we have done that, it's better we have our answer in standard form. So extension is equal to 1 times 10 raised to the power minus 4 meters. So now that we have our extension, we can now solve for the force constant. Force constant is equal to applied force over extension. Applied force is 20 and our extension is 1 times 10 raised to the power minus 4. So our force constant is 20 times 10 raised to the power 4, or we say 2.0 times 10 raised to the power 5 Newton per meter. Okay, so we are done with solving. So let's go over to the next example, which says that a spring has a length of 20 meters when a mass of 30 kg hangs on it. A spring has a length of 20 meters when a mass of 0.3 kg hangs on it, and a length of 0.5 meters when a mass of 1.95 kg hangs on it. Calculate the force constant of the spring. Calculate the length of the spring when it is unloaded. Now let's write out our parameters and then have a clarity of where to start from, on what to do, what to solve. Okay, so this spring has this length when a mass hangs on it. That means this is not the original length. This is the length when a load was on it. So we are going to call that one L1. L1 is 0.20 meters. And then this mass that was hanging on it at that point, we call it M1, 0.30 kilograms. And this length when this mass hangs on it. So that one we are going to call this the length 2, 0.75 meters when this second mass M2, 1.95 kg, hangs on it. And we've been asked to calculate the first constant K, and later we are to calculate the length of the unloaded spring, that's the L0, the new length of the spring. That one will be for later. Now, how do we proceed? Okay, so we already know that K is equal to F over E. So we need to find the force. So we've been given that G, acceleration due to gravity, is 10 meters per second squared. So we are going to be converting all these masses into weights, that's forces. So we have that F1 is equal to M1G, which is 0.3 times 10, giving us 3 Newton. We have that F2 is equal to M2G, which is 1.95 times 10, giving us 19.5 Newton. So having seen this, what again do we need? Okay, extension. We have that extension will be equal to whatever length we have minus the original length. So let me just say L sub x minus the original length. So where x is either 1 or 2. Okay, so now we are going to proceed. We have that force is equal to KE. So this is force 1, force 2. We are going to form two equations. We have that force 1 is equal to KE1. Okay, E1 will now be L1 minus L0. And then E2 will now be equal to L2 minus L0. So this is F1 is equal to, okay, F2 will now be equal to KE2. Okay, so we are going to substitute. And now I've copied everything into this place so that we can have enough space to solve everything we needed to solve. Okay, so we have these two equations. Now let's start writing them out. We have that, okay, let's write out equation 1, that is that F1. So let's write the equation for F1. Okay, our F1 is 3 Newton. We have it as 3 Newton is equal to K. The constant of the first constant for every material is the same for that same material. Since the same material is the same, so K is K. There is no K1, there is no K2. We have E1. E1 is length 1, which is K into E1, which is length 1, 0.20 minus the original length. We don't know it. That's part of what we're looking for. And we call this equation 1. For equation 2, we have F2, which is 19.5 Newton, into K is equal to K, L2, which is 0.5 meters, minus our original length. So this is the extension 1, this is the extension 2. We call this equation 2. Now, what we're going to do is we can decide to open up the bracket. Yeah, that's what we're going to do because we have simultaneous equation and we have two unknowns. So we're going to use elimination method to solve this. We're going to open up these brackets. So when we do that, let me start with equation 2 so that it will be easier for me to subtract, because you know the bigger equation is going to subtract the lesser one, or else we're going to have negatives, and we don't really want to work with negatives. They are really confusing. Like nobody wants to work with negatives. Okay, so let's start with the second equation in opening up the bracket. So we start by saying 19.5 is equal to 0.75k minus LOK. That is, this multiplies out. And then we have this one as 3 is equal to 0.20k minus LOK. And in this case, what we needed to do is to eliminate this since they are of equal value. So we eliminate this by subtraction. All we needed to do is subtraction. Why subtraction? So that when there is negative here, negative becomes plus. So minus this value plus this value is saying like this minus this. So it eliminates. So we're going to say, we're going to do equation 2 minus equation 1. So we have our negative here. 19.5 minus 3 is 16.5. 0.75 minus 0.20 is 0.55k. And this becomes minus this plus this becomes 0. So this is what we have left. We have to divide both sides by 0.55 so that k can be standing alone 0.55. We cancel out, and at the end of the day we have that the first constant k is equal to, let me get that, 30, and its unit is Newton per meter. So we have gotten the first thing we were asked to solve for. Now the next thing is for us to get the original length. And to get the original length, we use either equation 1 or equation 2. So let me use equation 1. Any one of them you use, you can get the original length. All we needed to do in the equation is just to substitute 30 for k in any of the equation we decide to use. So let me repeat equation 1, which says 3 is equal to k into 0.20 minus LO. Okay, so we have 3 here, and instead of k we have 30, and we now have 0.20 minus LO. We can decide to open up this bracket, or we can decide to divide both sides by 30 so that this bracket is still open. So I decide to choose the easier one, dividing both sides by 30. When we do that, we are going to see 0.1 is equal to 0.20 minus LO. So we are going to send this over to this side, right? Or we can decide to send this over to this side or here. But if crossing so many times all at once is confusing, let's just send this over to this side. We have 0.1 already on this side, and then we invite 0.20. It comes over to become negative because it was positive here. It's equal to minus LO. It was here already as minus LO. Okay, when we do that subtraction, we're going to get minus 0.1 is equal to minus LO. Minuses will cancel out each other. We now have that the original length is equal to 0.1, and its unit is meters, because remember we converted everything to meters originally. You can decide to multiply by 100 to get it as cm, but anyway, everything was in meters, so it's still in meters. So that is how that question is solved. Okay, we now have this question. A force of 40 Newton applied at the end of a wire of length 4 meters and diameter 2.00 millimeters produces an extension of 0.24 millimeters. Calculate the stress on the wire and the strain on the wire. And we are to use pi as 3.14. So for this case, let us write out the parameters we have. Force is 40 Newton. And the wire of length, so original length of wire is 4 meters. The diameter of the wire D is 2.00 millimeters. Let's convert that to SI units already. So millimeters, to convert it, we divide by 1000. So we are going to have 2 times 10 raised to power minus 3 in meters. Okay, produces an extension, so we still have extension is 0.24 millimeters. We convert to SI units meters by dividing by 1000. We're going to get 2.4 times 10 raised to power minus 4 meters. Okay, and then we've been given that pi is equal to 3.114. Okay, we've been asked to calculate the stress. Remember that stress is equal to force per unit area of an extension of an elastic material. So we already have force. We need to get the area. So area, this is a wire. The cross-sectional area of a wire is a circle. Like when you look at the face of a wire, it's a circle you're seeing. So it's the cross-sectional area of a circle. The area of a circle is equal to pi r squared. And we've been given the diameter. So we can as well go over to divide this into 2. So giving us 1 exponential minus 3 as the radius. So that is what we are going to solve with. 3.14 times the radius. The diameter was 2. Its radius is going to be 1. So the area of the wire is 3.14 times 10 raised to power. Oh, it's squared, right? Squared, so minus 6 meters squared. Okay, we come over to this place to get stress. So this is 40. The force is 40 Newton over the area, which is 3.14 times 10 raised to power minus 6. Okay, when we get that in our calculator, we are going to get 1.27 times 10 raised to power 7 Newton per meter squared. That's force per unit area. So we have gotten the stress. Now we have to calculate for the strain. Strain is equal to extension over original length. Now we have our extension and we have original length. So we just substitute. Extension is 2.4 times 10 raised to power minus 4. And original length is 4. And when we solve that, we are going to get that the strain is equal to 6 times 10 raised to power minus 5. Now, strain does not have a unit. Can you tell me why it doesn't have a unit?